Okay, so today is 7.2. So what we'll talk about today is the second in our series of 3 that talk about site investigation. So last time we talked about the fact that we may be interested to understand what's underneath our feet. The first way to do that is to be able to drill holes. If we drill holes with an auger, we can penetrate into soil. If we drill holes with a rotary drill that is a tricone bit or a hammer bit, we can go into soil or rock, and we don't typically get samples from those. Or if we go into rock, we can drill with a rotary rock core and recover samples. And so we talked about those different methods of being able to advance in those different materials. So 7.2 is to talk about what kind of sampling we might want to do to see what physically is in there, retrieve samples, retrieve fluid samples, be able to measure permeabilities, for instance, would be included in this. And then the third part is to talk about if we know what is present along these very slim lines where we have boreholes and aren't necessarily representative of the full site, how do we extrapolate between boreholes? And so geophysics would be the way to do that. And geophysics is just a way of being able to use some proxy parameter that you can pick up remotely. So it would be seismic velocity, the dielectric properties of the soil measured by radar, or electrical properties of the soil, resistance, and use those as a proxy for the materials that are there to be able to map out the stratigraphy. And so that would be the third part that we'll talk about. So that's the third one, which would be Thursday. And then I guess I put it online. Last year we had one of your predecessors come and join us. His name is Jason McNew, good guy. Was in this class, I think, about 20 years ago now. And he gave us a talk last year. So I'm assigning the recording of that a week today. And so it's quite an easy quiz. I think the quiz says you did or didn't watch the movie. so have a look at that, and that will be our last activity. And then a week after that, 2 weeks today, a week next Tuesday, is the midnight deadline deliverable for your stuff. It's kind of a hard deadline because I need to take your videos and your quizzes and start uploading them. So it's, out of all the deadlines we've had, it's probably the need to be the hardest of all of them. So it's kind of a firm deadline. So that's kind of where we are now. So let's talk a little bit about sampling and being able to understand exactly what's going on. So I made the point already that when we talked about drilling, we talked about different methods for soil, augering and rotary drilling, and different methods for rock, rotary drilling and diamond drilling, and they were only applicable to those different environments. Certainly with auger boring and with hammer drilling, we don't recover samples. So how do we go about getting samples from the subsurface that tell us something about what's going on? So that's our first job. The other question that we have, I guess, is that once you go to the expense of putting a drill hole down, which is quite expensive, $10 to $40 a foot, maybe $100 a foot. You saw some drill holes on the island of Montserrat in the Caribbean, and it turned out that those 4 200-meter drill holes end up costing $800,000. So they were literally $1,000 per meter. That's not normal drilling, it's just because it was in an exotic and unusual location. But if you're drilling a hole, you might as well do something with it to be able to recover things like fluid pressures, which you want to be able to define flow rates across an aquifer, or not across an aquiclude, which you'd like it to be excluded, and the ability to be able to take water samples for water quality also as well. So we'll talk about that. And then in addition to that, we'll talk about another method of being able to probe what's going on, which is referred to as direct push methods or continuous profiling. They only apply to soil, and you'll understand when we talk about them why they only apply to soil. So that's it. So sampling, you'd like to be able to get some samples to take back. And so the the division of different materials that we talked about, soil, obviously very soft and easy to probe, versus rock, much harder and much less easy to probe, is the main division of the different techniques that are used. If you're talking about soil sampling, then there are two methods that could be used, kind of epitomized in this little cameo picture here. And that is either in what would be referred cohesionless, so cohesionless soils would be silts and clays. No, sorry. Scratch that. Cohesionless would be sands. Okay. And cohesive would be clays and silts. So I don't know if you know the makeup of soils, but they're all based on grain size. So clays would be less than 200 microns, I think. Silts would be larger, sands would be larger grains, millimeter scale grains, gravels would be larger. And the difference between these materials is that sands actually are quite resistant to being things pushed in them, and clays and silts are much easier. So the main sampling methods are similar in that you're basically pushing a sampler into something that exists at the bottom of your hole. So you've augured down or you drill down, you've pulled all your drill rod, you've entered your sampler down to the base, and then you either push it in slowly and constantly under a constant weight and hope that you can pull out a cookie from that when you twist it off, or you physically bang something in that also has an interior hole into the soil. And so in sands, you use something that's sometimes referred to as a split spoon or a split barrel. I guess these two things here are those. And we'll see some pictures of it, but you can imagine from this that it's a cylinder. It is a split cylinder, so that if you take this shoe off and take it out of the top, it breaks into two halves. And the idea is that you enter it down to the bottom of the hole, so the bottom of the hole sits here, and then you physically just bang it into the ground. And as you bang it into the ground, the soil advances up into it. When you've advanced it, it's usually about 1 foot long or 18 inches long. When you've gone that far, you perhaps twist it, or you just drag it up the hole. And this little ball cock here, this ball bearing, serves to close the valve so that any water that's held up in the hollow drill string above, as you pull the sample out, it doesn't wash the whole sample straight out of the system. And so very rudimentary. And the idea is that because these are quite hard to penetrate, you physically bang it in with a monkey hammer, and we'll look at that in due course, so you'll see. And so when you get it to the surface, you bring it out, you take the shoe off, you take it out of the arrangement, and you break it open, and you take the sample out, you bag it, and do something with it. So in sands, you use something like a core barrel. In clays, and so this is another one here. So these are all different varieties, different lengths, different diameters, etc. But basically the same idea. It's a barrel that's of some length that you get a disturbed sample. So the sample gets pushed up in here, and actually it's quite disturbed. So you always just take a grab sample, has no structure in it of the layering that might have been present in situ, and you bag it and then take it back to the lab. Maybe you sieve it. Do you do labs with formerly Mark Klima and now with someone else that do sieving? Do you do a sieving lab?
Yeah.
On sieves, meshes? Yeah, same deal. So that's how you classify soils. In things that are soft and fine grained, like silts and clays, you'd use what's referred to as a thin wall sampler. So the wall of this is this part here, which is pretty thick. So 1/4 of an inch plus. A Shelby tube is a thin wall sampler. You can cut yourself on the thing. It has no shoe at the front, and it's placed at the bottom of the borehole, just like this sampler is, but instead of being banged into the ground, it's just physically pushed into the ground under the weight of advancing the the drill rig column. And so it pushes in, the cookie cutter pulls the core, just gets pushed up into here. Once it's up here, you twist it off to break it off. And again, you have a ball bearing in here that stops all the fluid in the drill stem pushing out the core as you drag it up to the surface. And so those are the methods by which you take samples in soils that we've talked about. In some cases, the undisturbed samples, so this is referred to as a thin wall sampler, because this might be something like less than 1/8 of an inch in thickness. And so the sample that goes up here really doesn't get turned over, it actually preserves its structure and stratigraphy as it moves up here. And so this is sometimes referred to as an undisturbed sample. This is referred to as a disturbed sample. These are for sands and gravels. These would be for silts and clays. And I guess the one wrinkle on these Shelby tubes or thin wall samplers is that sometimes they're used with a piston. And the idea of having a piston here is that if you put it down to the bottom of the hole and then you physically push this cookie cutter beyond the bottom of the hole to get your sample, leaving this piston flush with the hole as the cookie cutter goes down around it, then when it comes time to retrieve the sample, because this piston now will be at the top of the sample, it allows you to kind of exert a vacuum. And that vacuum helps you keep the sample within the tube as you pull it up 10 feet or 20 feet or 100 feet up to the surface, and then take it off the sampler and then send it to the lab. And so typically, the other difference between these is the split barrel you bring to the top, you take the shoe off, you break it in half, you pour the sample into a bag. With this, you actually don't remove the sample from the tube. You break the tube off from the drill string, you seal the top and you seal the bottom of it with paraffin wax, and the tube actually becomes the sample holder when you send it back to the lab. And so this might not be an unusual thing to do as an entry-level person sent out on your first job. It certainly was for me. And we talked about core barrels, I guess, last time. And so I won't go through all the advantages and disadvantages in this, because we'll look at a bunch of pictures of these things as we go through, but these are the differences. So this would be a split spoon in this case. This is a shoe that goes on the front, which takes all the abrasion as you bang it into the ground. The sample goes up in here. This part of the tube unscrews from here, and breaks open to be able to retrieve your sample. It turns out that many decades of banging these samples into the ground, I don't know when this technique was invented, certainly more than half a century ago, is you can actually use the number of blows with a standard hammer to get it into the ground to actually say something about the strength of the material. And so the blow count that it needs to advance a foot is often used to do things like calculate the bearing capacity of foundations. Not relevant to this class, but that's what these tests are used for. So not just a way of recovering samples, but a way of actually testing the material that's in situ. The thin wall sampler is this, either without or with a piston. It's the same idea. This thin tube, this brass thin tube, is anchored to the tool here. The drill string goes here up to the surface and is physically pushed in to be able to retrieve a sample. If it's silt rather than a clay, you might use a piston sampler, because you can put a vacuum at the top of the sample to be able to hold it in there and then drag it up to the surface. And this one on the far right, if you look at the key, is a rotary sample from a coring bit, which we talked about last time, where the fluid comes down here, it gets diverted around the core barrel, comes out at the business end of the shoe, the cutting shoe, hits the sample here and gets returned up the other side of the annulus. And this central portion here that you see is the core barrel that's interior, that you can actually retrieve along the length of the sample. It doesn't look like it here, it looks like this thing's in the way, but you can retrieve the core barrel up through the sample without breaking all the drill string to come here. So one of the biggest costs in drilling, so if you look at, for instance, deep geothermal wells, the biggest technology change that's needed is that when you go down 4 kilometers and drill a well, if you're just using a tricone bit, then if you're drilling in really hard rock like granite, the bit won't last a single hole. You might use 20 bits to get down to 4 kilometers. So as soon as your bit wears out, you have to drag all the drill string up to the top, replace the bit, and then re-trip back down to it. So the big cost in terms of time is actually pulling the stuff up the hole and then re-entering it down the hole, etc. So along with this, in your first job on a drill rig, what you would typically do is you'd fill out a drill log. I haven't filled out one of these for many decades now, so I don't know whether it's on an iPad. Could well be. I hazard a guess that it's probably just done on paper because it's such an aggressive environment that using an iPad in the field probably isn't, it's not very friendly to it. But the idea is that you'd record much of the information of the drill hole so that someone else, perhaps doing a later design, can use that information to be able to figure out exactly what's going on in the subsurface. And so the things that you would record are things that would make sense to you, that would be able to define that behavior. So it merely is a log of behavior or items with depth. This is a Canadian one, so the depths are in meters from Golder Associates. I guess Golder still exists as a company. I think they've been bought out, but I can't remember who they have morphed into. I think they still exist. And so based on the samples that come out of the hole, there would be a log which would describe what it is that you see. And of course, the only way that you'd know what's coming out of the hole would be the drill cuttings, the material that comes on the auger as it comes up to the ground surface, or the samples that you've just taken using a split spoon in sands, or in this case, silty clay. It would be, this is probably what comes up on the auger. It's probably not a sample. So anyway, so you see a log of what you see. You're not geologists, but it's some description of exactly what's going on. It identifies when you go into bedrock here and the depths at which that occurs. It gives some kind of symbolic log for the different materials. It gives an absolute elevation for the collar depth and the depth below collar. It gives some information on the numbers and types of samples that you've recovered. So this would be RC. This must be rock core. This is actually, I don't know if this is for Smithville. I think it is actually. Does it say? Be about the right date. It doesn't say the location. Yeah, it would be the right date. I can't remember the Smithville, but I think it probably is. And so the other things that you see, the samples, their type. So you'd bag them and label them and note what they are. If you're banging a split spoon into the ground, you'd see that the number of blows that you apply to go 0.3 of a meter, Canadian speak for per foot, I guess, is recorded there. And none are taken in the overburden here. And then other things that are noted from the drill core. The recovery, how much as a percentage of the total core. So if you go forward 5 feet, how much of that 5 feet do you recover? Percentage recovery. How much of it's solid, not broken? The so-called rock quality designation, RQD, which is what percentage of the core comes out as pieces bigger than 4 inches, I believe is or 10 centimeters. Fractures per 0.3 meters in the rock. So this is number of fractures per foot. Information on those fractures. Are they horizontal, vertical, or do they have a dip in between? Horizontal would be 0 dip, vertical would be 9 degrees dip, and in between would be some variation on that. Descriptions of those discontinuities. Important, of course, because we've said that the fractures are potentially, the super highways for fluids to travel in the subsurface. And if there's surface chemicals like iron staining on it, it might be some indication, for instance, that those surfaces are hosting flow. because they've got to be deposited somehow, and flowing fluids might be the mechanism by which that occurs. Water contents that are measured in soils typically, the liquid limit and the plastic limit. Very bizarre experiments. The liquid limit is when a sample, you add enough water to the clay that when you put it in a little dish and you drop it about an inch for 10 times, a slit that you put in it closes up. Really rudimentary test, so-called Atterberg limit test. So the liquid limit is when it flows like a liquid. How much fluid do you have to get to it for it to flow like a liquid? And the plastic limit is when you take that clay and you roll it into a sausage, and you can no longer roll it into a sausage which is probably 1/8 of an inch thick, or perhaps it's 1/4 of an inch thick, I can't remember. And so you keep on adding water or drying it until that occurs. So the natural in situ moisture content is somewhere between this liquid and plastic limits, and that says something about the behavior of that clay that you'd expect if, for instance, you're putting a foundation on top of it, not for the things that we're interested in. We will talk later on about the fact that if you're spending $100 a foot to be able to put a drill hole down, you might want to make the most of it. And so the other thing that you might also do is you might use your drill hole ultimately to be a well. So either to sample from it while you're drilling it, or to be able to take water level measurements for it once it's done, or to be able to run injection tests in it using a packer to be able to look at the permeability. And so the other thing that's on here, which I guess is on the far right hand side, I guess if you see these dips here are measured in the core, and it looks like the dips of the bedding are, or the fractures are 90 degrees, so vertical fractures, which is interesting because if you have a vertical borehole, you tend not to pick up vertical fractures because you can't sample them very easily. Horizontal fractures you'll get lots of because they cut across the whole bore, but not. And I don't know if they did. So there are no measurements of permeability. So you could do a pump test in situ and identify the conductivity of the sample. So in other words, if you're going to go to a site, this is exactly the kind of stuff that we made into that little profile that you used in your assignment number 5 to look at Smithville. Information on the right hand side is in terms of completion. I guess this is the initial part of the hole was drilled by auger, casing was put into that, the casing was grouted in place, there's a steel riser placed within the casing, the water level at drilling was down here, a piezometer was placed in the bottom of this hole. We'll talk about that also. So you have a piezometer tube, which might be a 1-inch piece of piping that you'd see in your house, that is cut at the bottom to allow water into it, with sand dumped in the bottom of the hole around that, and then sealed with grout or with pelleted bentonite to be able to isolate this piezometer zone, which starts here and ends here at maybe the bottom of the hole. I guess not, it continues on sheet 2. So it isolates this zone from the rest of the borehole. So the flow regime that you're able to sample fluids from in this part, and to measure inflow or outflow from, to measure permeability, gives you permeability specifically for this portion of your well bore. And so it doesn't average it over the full length of the well, which might be many tens of feet, but it allows you to get something like a 6-foot length, 2 meters in this particular case, where it identifies that. And so you'd want to be able to record those data. So that's a typical borehole log that you'd have. Other things that you would do, we've talked about this here, that you might, at the bottom of your borehole, want to either measure pressures or actually take water samples. The standpipe piezometer we just looked at in this borehole is exactly this. It's a zone of permeable sand that you've introduced in the bottom of the hole, and you have a piece of plumbing that contacts that allows you to measure this elevation of the water within the borehole. So if you know what this is, you certainly know what the pressure is here. And so if you have a whole bunch of these boreholes and you know what the pressures are over your whole site, you have some way of being able to get the gradient of head, and you have some way of being able, if you know the permeability, to figure out what the advective and Darcy flow velocities would be. So these are by far the most common piezometers that are used, but there are other types of piezometers. Ones that are used above the water table, where you're measuring actually a negative pressure, tensiometers, so-called. And so they work a bit like a U-tube manometer. And so if the level of mercury or fluid within one arm of this is lower than the other, this by definition, you know, is measuring a negative pressure. And so in the unsaturated zone, you use tensiometers to measure the negative liquid pressures within the system. And more sophisticated ways, apparently, of measuring pressures would be to use pneumatic piezometers. So this would be a membrane which covers the edge of this. If you imagine that the pressure acting on this is the same as the pressure you blow in down here, no fluid flow will occur. It's only when this pressure acting here is larger than the pressure underneath that we bypass and go up the other side. And so the time at which the pressure overcomes the in situ fluid pressure is a measurement of the value that you have within the system. Same idea here. So different kinds of piezometers. And in some cases you can also measure things like flow within wellbores. These aren't very common. You can imagine that if you wanted to know where the water was flowing up your borehole, you could have a heater element, a filament that would heat the water, and you could have a heater sensor, and this would measure the rate at which water was flowing up or down in the system. You could imagine you could have an array of a heater with sensors all the way around that heater, so that if you had fluid flowing across a borehole, you could also kind of pick up the directionality of this. Or the more common way to do this would be with a borehole camera. You put the borehole camera in it, you look through the lens, and if you see particles being carried up relative to your viewing here, you know that there's fluid flow velocity either up or down your borehole to be able to classify what's going on. So all kinds of interesting features you can have, and some tables on what works well and what doesn't work well. So just to cement, no pun intended, just to cement those ideas, standpipe piezometers would be what we just looked at in the borehole log for the Smithfield site. Not necessarily restricted to just one level. You can imagine that you have a very deep borehole and you've come up and you've grouted it up to some level. Then you introduce this pipe. You then fill this with sand, and then you grout the top to seal it. And so if you keep on doing that as you retreat up the borehole, perhaps you have 4 or 5 of these individual zones at different depths, which would of course sample different parts of your aquifer, or aquiclude if it was. And of course you can pour water into these individual tubes. It will raise the water level within the tube, and if you look at the rate at which it falls, the rate at which it falls is some measurement of the rate at which it flows out of here. And so you can use so-called slug tests, because you inject a slug of water that raises the elevation. That slug of water bleeds off into formation over time, and merely if you monitor the height of the water with log time, it gives you a straight line relationship often, and the slope of that straight line allows you to get permeability. Very simple. I don't know if you talked about pumping tests or slug tests in 452, but you can get permeability from them. And of course the other way to do that is, instead of having an installation, which of course once you've put it in place it's not going anywhere, it stays in place all the time, you could use packers. And so what you could do is you could take an open hole, introduce in this open hole a packer with a so-called, that straddles a zone. And these packers are just fancy neoprene balloons. And they exist on a cylinder. They have a gas connection to be able to inflate the balloon within the borehole, to be able to inflate a lower one and an upper one. They're connected on the surface to an air cylinder or a nitrogen cylinder. And then when you get it down to the depth that you want, you merely inflate these two neoprene sleeves to push out against the borehole. They seal the borehole and isolate a zone, and then you can pour water into this zone just like you did in this packed off zone here, except of course this zone is usable for some time, say for 10 minutes or an hour, and then you deflate the packers, you withdraw them up 10 feet, inflate them, and then you could do a profile all the way along your hole, and then also leave your hole open to do something else with it if you wanted to. So packers are used to be able to do exactly the same thing you do with a standpipe. I guess of course once you take the packers out and you leave the well open, then the whole well is typically open all the way along its length. And so any water level that you measure within that hole is not really representative of any particular zone, because all the zones are amalgamated and mixed. And so also any water quality sample that you take is some amalgamation of the integration of fluxes along the full borehole. So those are the kinds of things that might get used in this. So, let's look at some pictures. So, what are some of these things that we talked about? Well, we looked at these last time on Montserrat. I forgot the name of this place. It's Forcemark in Sweden, which is north of Stockholm by a couple of hours. It's the Swedish low-level radioactive waste repository. What did we look at? Yeah, we looked at all of these. So we're specifically going to talk about sampling. So this is kind of where we left off. So this is exactly what we talked about. This is a piston sampler. So this is the piston that goes on the thin wall sampling tube. It exists along the length of the tube, and it's advanced along the length. You can activate it from the surface once it's deployed into the bottom of the hole. So this is the end of that piston. This end here is the piston. So what has happened is a long 18-inch brass tube has been placed over this end of this and anchored by some set screws here, which is this. So this is the end of the piston. So now the piston has been pushed out to its full extent. It's joined by a thin, maybe 1 inch or so spindle along its length. And now this assembly is the sampling tube. It's taken, it's put into the borehole, put down to the bottom, and then physically the cookie cutter is pushed into the bottom of the hole, and this piston is allowed to freely move up into the inside of this sampling tube as the sample gets pushed into it and therefore retrieves it. And the idea is if there's no air gap between the end of this piston and the top of the sample, then you have a vacuum which gives you a greater chance that you're going to recover your sample when you twist it off at the top and then the base, and then you recover it up through the open hole. And so that's a picture of the drill rig drilling. This is the sample. Lots of people thinking about this. Yeah, this is the open sample. So this is the brass drill hole tube. It's open. I don't know exactly what's going on there. Yeah. This is the piston. Here you see two little set screws. So in top of the brass tube, you put it over this coupling here. It has two holes in it, and you just unscrew these brass lugs so they become proud of this surface, and then they anchor the tube onto this mandrel. you see here. So perhaps, yes, actually it's quite good. So these holes here, you retract screws out into those, and that just holds the sampler in place. That looks like a sample retrieved. So this is the tube taken off. This is the coupling hole. This is the sample in there. I presume the sample comes up here. It's messy from people using gloves on it. This is the piston that's been taken off it. This is using a little Torr vane. So you can, must be a picture of this. This is a little vane. You see these a round surface with this little, it's almost like a water wheel, right? These little protrusions. Actually, you can see it best here. This thing is pushed into the soil. It's turned on this little implement that has a spring. It's like a torque wrench. When you exceed the torque, when you fail this little thing that the flats have been pushed into, when you fail it off so this round can actually move because it's exceeded the torque that you apply to it. The measurement of the torque that's recorded on this little dial here gives you some ballpark appreciation of the strength of this clay. Pretty rudimentary, but a quick and dirty way of doing this. So-called Torr vane, Torr for torque. And then I mentioned that once you have the samples, you don't retrieve the samples from the tube on site, you merely seal it. So this is paraffin wax melted with a tiger torch, paste in the open Shelby tube to seal the moisture in. This is the thing that attaches it to the sampling thing. And you'll do this at the top. You'll pull some of this soil off here, so you recede it back maybe a couple of inches, and you'll seal this end as well. So this end and the top end are both sealed with paraffin wax, and you send it off to the lab to do whatever you want to do with it. So
Is
pretty.
this still in Alaska?
This is in Massachusetts. No, the other stuff was never in Alaska. It was in Northwest Territories, but it was in the Arctic. This is below a overpass in Massachusetts, somewhere north of Boston, on this particular rig.
Yeah, I was going to mention last class that I'm taking a gen ed like inner domain, and they were the first module was about this core sampling and how they're used to determine the climate of the Asian climate, and how there's this ship that goes around the world. Taking samples from the ocean bottom. Yeah,
there's many of them. Joides resolution is one of them. The NSF one. The U.S. has them, but most every country has. Certainly the Japanese and the U.S. Yeah. So there's a big program of the so-called ocean drilling program to take samples, just like tree rings, right? That's
the
Joides resolution is one of them. Yeah, and so yeah. So that's much more sophisticated. So sampling from those things probably might be at 2 kilometers deep in the ocean, but the same kind of principles apply, that you try and get a high quality sample that you can recover, and then you typically retrieve it from these core holders, thin wall core holders, and then you slice it, and then you'd be able to look at the individual laminations, which represent different years. Sample them. Get different isotopic analyses to be able to date them, etc., and then be able to figure out what the climate was. So the stuff that we did in the Arctic Circle was not related to that either. So this is a tube, same things. I guess pulling out the set screws. This is the end of the sample. This is the Torr vane, just a torque wrench. Good picture of it, actually. Okay. What else have we got? I'm trying to think. I can't remember whether I had. We had some Boston pictures. So I wrote on here Boston 12 minutes. So we're doing okay. So. You can imagine the noise. This is how you can look at your YouTube videos, 5-speed, perhaps 30-speed. So this was an experiment where the drill rig was used. It was actually used to test out a new tool to be used offshore in the petroleum industry. So the idea is that when you drill down into the Gulf of Mexico, you want to know exactly what the pressure is ahead of the drill bit, but you don't get that because of the big volume of the fluid that's in the well. So this was an idea to have a probe which could be entered into the drill well and then pushed beyond the end of the drill hole to be able to measure the actual pressure. So what this tool is to have something that looks a bit like a pencil. I'm sure we'll see it. And it was just retrieving it. Does it ever get put down somewhere where we can freeze the frame? No, you get the idea. So you lose it. So you can see here that there's something about a bit longer than the length of a pencil, probably thinner than the length of a pencil, and right at the tip it has a pressure transducer. So the idea is you could push this down the hole, at least you could get beyond the edge of the hole by this amount, the length of the pencil, to be able to get a pristine measurement of the pressure that you had. And so it's more of a scientific project to be able to evaluate that rather than a straight site investigation. There you go. It bent. It's not very durable. And ultimately it was deployed, 2,000 feet into the Gulf of Mexico. And so this was just a drilling rig that was used to be able to sample that. And so I got on my list that it's at 12 minutes. So what happens at 12 minutes? People taking pictures of themselves. Yeah, okay, you can see what's going on. So this is the drill hole here. You can see the drill string going down into the hole. This is just a 90-degree fitting like you'd have within your house to be able to take the return water that comes. So the water comes down the drill string, goes down to the end of the bottom of the borehole, comes up the outside of the tricone and is caught by this here, goes into this bucket. I want to get rid of this. Goes into this bucket, and I can't see. Oh yeah, and this is the suction from the bucket that goes back up into the drill string. So it's completely a closed, kind of a closed system. So the return water that you used is used as the new water to inject down here. So this is it. So the drill string, so all conical threads so they're easy to break open. This piece of string is just so that you can seal the fluids into the drill string as you put it down. This must be pulling pipe. So this is drill steel. The bit is on the bottom. You pull it up into the mast. You have this little doodad that anchors it. You unscrew another piece. You pull it up. And so breaking pipe to pull it up the hole is what takes a huge amount of time if you want to retrieve your sample or to change out your drill bit at the base, because you have to break every single one. And then you have to put it back down with a new drill bit on, and then you drill some more. Actually, that's a tricone bit right there. Yeah, as soon as I freeze it, it goes kind of fuzzy, but this is a tricone bit. So this is the bit that's been retrieved. It's been connected to the drill rig by drill string, which is all these look like 5-foot lengths of steel. If we end up looking at it, yeah, there you go. So these are these 3 tricones. They're not motorized, but they're on spindles. And when you push it on the bottom of the hole, it just runs over it like a car wheel. And the individual pieces, which are stress concentrations on the tricone bits, allow it to break off pieces. And those pieces are washed back up the hole with the return fluid to the surface. So I'm doing something, okay. So that's on double speed. Not sure what's going on there. It looks like, okay, it's a monkey hammer. All right, so you didn't see the split spoon, but down at the bottom of the hole is a sampler. The sampler we talked about that we used in sand and gravel, which is sitting on the bottom of the hole. And now it's being rammed into the bottom of the hole by this monkey hammer. I call it a monkey hammer. All it is a weight, a capstan. When you pull on the capstan, it tightens around the capstan, and therefore it gets lifted up into the rig. When you let go of it, it falls under gravity, and the specific weight of this falling through a specific height is what you measure. So you're measuring the blow counts, 10, 11, 12, to be able to drive this a foot, and that gives you some impromptu measure of the strength of the material. And of course, after this, you're left with the drill hole to be able to do it as you wish. So I don't know if there's anything else in this or not. Yeah, you see it. So once you've seen this once and done it once, you know exactly how to do it. Piston sampler again. Let's bring a sample. I think this is measuring exactly how deep it goes into the hole. I can't remember exactly what we're doing there. But that's me in the brown with my natty. It was December in Massachusetts. Yeah, and that's the sample coming out. This looks like it has no shoe on it. This is just the end of the brass tube. It looks like it's hit a rock and got buckled over. But this is taking that off from the system. Yeah, you get the idea. So, that's the idea of drill rig. Again, once you've seen and done these things once, you know exactly how to do it for all time. We talked about three things. One would be drilling and sampling. The second would be instrumentation, so packers, which we'll go back to and talk about. But the other one is using direct push methods. And so the other opportunity we have, instead of being able to drill, is to physically push something directly into the ground and to measure its resistance to being pushed into the ground, and maybe also measure a couple of other things. So these kinds of rigs, not a very good picture here. We'll look at them in more detail. They come inside a truck. Some of them are on little Caterpillar tractors, which are like a little bit like the Caterpillar tractor you might have on a snowblower, that kind of size, maybe 4 feet in length. And the idea is that we'll see how it works. The idea is that within this truck, you can take a probe which has 10 square centimeters cross-sectional area, so it's probably about 1 inch in diameter, with a conical tip on it that looks a bit like this, that is physically just pushed into the ground at a constant rate. It's pushed into the ground at 2 centimeters a second, and this cone has 3 important pieces of instrumentation on it. It has a load cell immediately behind the tip, which measures what force is applied on the tip. It has a load cell behind this sleeve, which measures what the force is that you have to push it with to move this sleeve through the ground. And it would typically have a pressure transducer that measures the pore fluid pressure that is generated as you push this thing into the ground. So as you push it into the ground, you get a continuous record of the forces that are applied, the pore pressure, so the tip resistance would be the resistance to this cone going in. The friction ratio would be the sleeve friction that would be applied on the side of this sleeve as a continuous profile. And the pore pressure that you measure here would be a continuous profile of this. So this means that at any particular depth that you find yourself, you have a measurement of the tip resistance, the sleeve friction, and the pore pressure. And if you take these 3 variables and plot them at any particular depth, the end bearing, the friction ratio, and so if you know what these values are for each of these at any particular point, then you can come up with a magnitude of a proxy soil that has these characteristics. So the behavior of different soils have different cone-bearing resistances and different friction ratios. And so if you measure those with depth by proxy of the forces that you have to apply to be able to push these into the ground, and also the pore pressures that get generated as a result of this. So at the same one, you'd have a cone bearing of this amount, I guess, on the top figure. If you also had a pore pressure ratio that was generated, you'd know that you're in this particular soil here. And hopefully they match up with the same numbers on each one of them. So these numbers just relate to a description of what the soils are. But you can also use it in a more quantitative way, for instance, to be able to measure permeability in situ as a continuous profile. And so these kinds of tools are actually quite broadly used. And so we have some pictures of these, of course, that we might look at. And they are here. I'll look at the other one first in my photos. So the first one's here. So this is in Sakarya in Turkey. This is where I don't know, 1998, there was an earthquake that I bet you it killed 20,000 people, unfortunately. And this is a direct push rig.
Oh, that's the movie again.
That's the movie again. This is a direct push rig. I'm not sure. Yeah, okay, you can see what's going on here. So this is the idea. So you have this little gantry here. You have a crosshead that is able to take these pieces of drill tube. They're probably a meter long. They're hollow. The data cable gets passed along the interior lengths of these tubes, and then they're used to physically push this conical probe. So you can guess this is to saturate. This is a porous element at the tip. There's a load cell behind here that measures the force that's applied to that load cell. There's a load cell here that measures the force applied to that. So you can separate the load that you need to push the cone forward versus the frictional load on this sleeve. This is saturating it. This is a condom that's actually on here to be able to saturate the filter so that it doesn't have any air in it, because it'll give you a wrong reading. And then this whole assembly is physically pushed into the ground at the head of this linkage of steel pipe, and physically pushed into the ground at 2 centimeters a second. So you'll see some pictures. So this is the cone right here at the business end of this. This is the drill steel, looks like a meter tall. It's placed into this rig. This rig physically just pushes it into the ground at 2 centimeters a second. When it gets down to the bottom of travel, you've already added the next link on. This head then quickly comes up to the top, grabs the thing again, and keeps on going down. And so you can see you can move these inside buildings for contaminant hydrology type work, very transportable. You can see what's going on here. And what they were doing, they wanted to know what the material properties were of these sands. All these sands liquefied during the earthquake, and so all the buildings that were built on them collapsed, and people who were in the buildings perhaps didn't fare so well. And so you get the idea. Don't pick your bottom if someone's filming you. And so you see what's going on here. See, it's getting pushed down at 2 centimeters a second. These are the spare tubes that will be added. I guess they don't have the data cable threaded through them, so the ones on the ground are the ones that would be used. I'm not sure if this goes down to the end of the run. No. You go down to the end of the run, you add the next tube on as it's still going down, and then as it hits the end of the run, you quickly take the turntable up to the top, grab the top, and then keep on going down. It's very, very straightforward. So these are made in the US by a company called Geoprobe and others. geoprobe are out of Salina, Kansas, and they're quite inexpensive compared to drilling. And of course, with this profile, only will work in soils, of course. With this profile, you can say something about the material that's present in the subsurface. So that is one form of these. Another form of these is one that they have. This is Roman Ritsu, a colleague of mine at the University of Michigan, a name that has not enough syllables in it, and he's topically of Ukrainian descent, from Kiev, I think, originally. And this is another one of those rigs, not mounted on a transportable platform. Well, it is transportable, but not as small as the other one. This is a truck-mounted platform. And the wrinkle on this particular implement, you see it exactly here. This is a piece of bicycle inner tube wrapped around the element to keep it saturated. As soon as it goes into the ground, it'll just get ripped off by the ground passing around it. This is the load cell at the top to measure the two loads of the tip and the sleeve friction, which we can use to be able to define as a proxy for the material we're going through. And this is dithering over putting it into the ground. And yeah, okay, so you can see, doesn't matter. So this is the stanchion that's pushed down to push it into the ground. This is a TV. So the different thing about this is it's called the vizcone. So what it does is it also has, as it goes into the ground, it has a small window in the side of it. And the idea was that you can use this window to see what the soil is that you're going past. And instead of doing a grain size distribution, maybe digitally you can figure out exactly what the grain size distribution is within the subsurface. And also, if you have non-aqueous fluids, you can also see them moving around in the subsurface as well. So that was the whole idea of this. So I'm going to try and, so this is exactly that. So you can't see it here. This is 2004, so 18 years ago. You were alive at this time. And this is just an old TV screen. You'd probably use something a bit more fancy these days. Well, you'd use a tough book to be able to record it. And see some pictures of it. Lots of people standing around, lots of people chatting. Yeah, being pushed into the ground. Yeah. So yeah, you see the thing being advanced 2 centimeters a second. You take another tube, you screw it onto the top. Again, all of these are conical kind of fittings, so they screw up easily and unscrew easily. And then as you push it into the ground, you just replace it. Okay, this is the business end of the cone at the bottom. Here's a little window with a sapphire glass covering on it, and it just has a CCD inside there, just like you have in your phone or in a camera that takes video of what you're going past. It's behind the tip by exactly, I think, 1/2 meter, and so you see what the tip sees in another 1/2 meter divided by 2 centimeters a second later, and so you can coordinate the exact location. This is getting ready to be deployed. It has the bicycle inner tube around the tip of it. And again, lots of people standing around. Sitting in a hotel room at the end of a busy day, drinking beer probably, was what I saw here. Yeah, very, very straightforward technology. Not rocket science. I don't know what that's all about. Yeah, pretty interesting piece of kit. So Roman developed this. It was his brainchild. It's quite a clever idea. Never really caught on in a big way, but the idea is pretty straightforward and somewhat appealing, I'd say. I'm looking for a better picture of the kit. Yeah, this is kind of interesting. This was at a, it's in Delaware. It's a petrochemical plant. And so they spoil all their waste into these big tailings pools. And so this was one of those pools that I drove my Jeep onto it to go and sample, and then they drove the truck onto this. But these ponds had completely solidified, so this was a field you could drive a car on. But as soon as the big heavy cone truck came on with the bass low frequency vibration from the engine, it liquefied all the material. Fortunately, not all the way to the surface, because the truck was on there, and my truck was on there at one stage as well. But basically underneath here, it's just like a spring mattress. And so probably I could imagine there'd be a foot of solid crust, which is dried out here. Below it is water saturated wastes that have been just, silts and clays that have been spilled into these ponds, left to drain, and they've drained out through the top and bottom, but they have relatively high water content, so that when you shake them, they compact. As they compact, the pore pressures build because you have the same amount of fluid in a smaller pore space, so the pressure goes up. That's my car at the time. We almost could have lost it, I suppose, but we didn't. And it liquefies. So that's that. And so that's that. So you see some of these. What else? I guess the one thing that I was going to show you in addition to this was a packer from an underground site. So here's one here for sure. I thought I had a better picture than that actually. Yeah, here. So this is exactly what an inflation packer looks like. So here is an aluminum mandrel with a neoprene sleeve on it. If you look at one end, you can see that there are supply lines to supply pressure to inflate this balloon on top of the mandrel. Put it down the borehole, inflate it against the walls. You have two of them so that you have a zone between them. The lower packer is linked by a gas line to the upper one, and also has a zone, and you're able to inject fluid along the boundary between them. And I guess the other one that we saw was one that was actually set up to do that. Here. So this is the, upper or lower packer, the gas line that links them, and this is the area where you either measure pore fluid pressures somewhere in this zone, or you'd inject fluids into the straddle zone. The straddle zone would be the zone between the two packers. Packers inflate against the wall, so they don't allow water to go up or down the borehole, and so the only place it can go is into the wall of the rock, and you can measure permeability with that. And so these are just a variety of different site investigation sites around the world, different locations. You've seen this. What is this? This is the Korean radioactive waste experimental site. So it's about an hour south of Seoul. And many countries have these exploration sites to be able to look at flow and transport in the subsurface, not for DNAPLs, but to look how fluids would go relative to locations if you put hot radioactive waste in the ground, and so to do experiments. This is in Korea. I'm pretty sure this is in Mizunami. This is in the Japanese Alps. Again, one of their two potential sites. So, Nagano, were you around for the Nagano Olympics? You might have been young. Certainly it was in your lifetime. The Olympics were in Nagano in the Japanese Alps. Yeah, if you've ever been to Japan, they've got some of the best skiing in the world, just like Utah powder, because all the cold winds coming from Siberia have no moisture in them. They travel across the Sea of Japan, pick up moisture, and then dump it on the mountains here and in Sapporo. And so I guess this is Mizunami. Again, an experimental site where you pump fluids in and you look at the transport properties by injecting tracers, seeing how quickly those tracers arrive at different locations. This is another such site in the Jura of northern Switzerland. Again, looking at radioactive waste disposal in clays in this particular part. A whole bunch of experiments in here to look at running tests, running hydraulic fracturing tests, looking at transport tests, looking at sealing boreholes with bentonite, all kinds of things. About an hour from Zurich. So this is a place called Monterrey, and this I think is Grimsel, which is another experimental site for radioactive waste disposal, again in Switzerland, but actually in granite, somewhere in the Swiss Alps. I don't know. I'm surprised if you're underground, it actually gets a signal to be able to locate where you are. And so this is in the Swiss Alps. Looks like it's very close to the, well, it is close to the Italian border. Again, about an hour south of Zurich. And again, to run lots of different experiments using rock coring, using sampling of rock cores, using packer testing, using dedicated boreholes to look at transport processes, and to be able to understand something about flow and transport in the subsurface. So I don't know if there's anything else other than that. So we could have an international tour, but we don't need to. Yeah, so anyway. And that's probably it. And so, yeah. So those are the three things I wanted to talk about, which are relevant for today. So we talked about drilling already. We know that we use different drilling methods in soils and rocks, and we know what those are. If we're drilling, then we'd also like to be able to make the best use out of the borehole by sampling. Sampling is different between soil and rock, as we've seen today. If you're leaving something open, if you leave an open borehole, you typically are required to seal it, so there's no cross-communication between portions within aquifers and across aquicludes. And so one useful way to seal it would be either to case it, so that the casing takes care of that sealing, or to put instrumentation in it, which only allows access to discrete zones. And so putting some instrumentation, I guess, benefits you twofold. One, you've completed the hole so it can't leak between different aquifers, which EPA or DEP wouldn't like you to do. And also with the instrumentation, you have the ability to be able to get pore pressures and water quality samples out of it to be able to say what's going on within the system, to define the behavior initially, and also to be able to say what's going to happen in the future if you try remediating it. And then finally, only for soils, we can use continuous profiling. And the advantages of continuous profiling is it's really fast. And so you can probably push a hole like 2 centimeters a second, you can work out exactly how long it takes to go down in depth. So in half a day, you can probably go 100 feet down and have a profile on that. And you can use that profile to say something by proxy about the materials that you've gone through, and perhaps be able to say something about their physical characteristics like permeability. And I'm pretty sure that some of these profiling tools allow you to leave the tool in ground and to leave a piezometer at the very base of it, which can then be used for the same things that we've talked about previously. And so that's it.